So good afternoon to you all. Myself Anil Kumar. I am again with you in this short course on GNSS or satellite-based navigation and journey from GPS to mobile phone platform. For me today is the last lecture, and the topic of the lecture is satellite-based augmentation system, which I'll be including the different systems, including the Gagan also. Gagan is basically designed for India and its surrounding area. So here, if you see already in the previous lectures, I've already mentioned that global navigation satellite system, or in short GNSS, means which is incorporating the global navigation systems like USA based GLONASS, QZSS, Compass, Galileo, and so forth. If you see GPS based, it has a dedicated augmentation system which is working worldwide, and it is called space based augmentation system. But initially, in short, here this is called SBAS, but initially this was called GBAS. So just there was some call. Sorry for that interruption. And if you, I was just talking about SBAS. Initially it was started as GBAS. G means ground-based augmentation system. So once people were knowing to use ground-based augmentation system, later they have switched to satellite-based augmentation system, because ground-based augmentation system can cover small area, say 100 kilometer, 200 kilometer, not the very big region like up to country level or including a few countries, the neighbor countries. So to reach to the larger area coverage, people have gone to space-based augmentation system. If you see USA-based system, it has dedicated augmentation systems working in different regions like VAS, EGNOS, MSAS, Gagan, GRAS, CDGPS, and so forth. Initially, they have gone OmniStar, which is again ground-based augmentation system, or Starfire. And we can just see again as a recap of the previously covered global or regional constellations. If you see global constellation, USA based system has 24 satellites, GLONASS 30 satellites, Galileo 27 satellites, Compass 30 global and 5 regional. And with these, if you focus on satellite based augmentation system, there is VAS, which has 2 + 1, 3 satellites, MSAS 2 satellites, IGNOS 3 satellites, Gagan with 2 satellites, and SDCM 2 satellites. One is as a spare and secondary is to distribute the or transmit the corrections. And there is I have also talked in the previous lecture regional constellations of satellite based navigations like QZSS for Japan and IIRS for India. So if you see, I've also talked about GPS based errors which are present in these systems. The error can be due to satellite orbital parameters, multipath error, ionospheric error due to ionospheric layer, clock drift, error in the clock of the satellite, tropospheric layer, which is basically water vapor and the dust content present in ionosphere. There is charged particles, and the receiver at the receiver end, receiver error, how the receiver is set up, multipath problem, receiver noise, and so forth. So these all factors affect the GPS signals, and finally we can see the effect in the form of accuracy. So with these factors, the accuracy what we get in XYZ coordinates degrade. So there is a lot of error in our XYZ coordinates. We should handle these parameters very carefully, so that the coordinates what we get XYZ are of very high accuracy. So satellite based augmentation means its availability, second is integrity in the data, accuracy and continuity. So it is continuous, it is accurate, it is integrated, and it is availability. And that is the role of SBAS. Overall, we get the data with very good accuracy. By default, without doing anything, we get the data of say 4 to 5 meter best accuracy is there. That means there is 4 to 5 meter error in our XYZ coordinates. But if we incorporate SBAS facility, that is basically GPS corrections through SBAS, so the error will come down to 1 to 2 meter without doing anything, just applying these corrections through SBAS. So three interone services we can see. For ranging, what I mentioned, there is a geostationary satellites, broadcast a spread spectrum ranging signal. Avionics adds like GPS link signal to the existing set of GPS measurements, and which improves the availability and continuity. Integrity means supporting ground network monitors the health of all the satellites, and it also prompts use and do not use warning broadcast via geostationary satellites. It improves the flight safety purpose. Accuracy wise, you can see ground network also develops differential corrections for all the satellites, broadcast via geostationary satellites along with integrity of the data, separate corrections for SV clock or SV ephemeris or ionosphere. Such a vector corrections is valid under continental area. So very vast area, up to very vast area, these corrections can be applied. So, and if you see, it improves accuracy from 10 meters. If you just doing observation, the best accurate data of 5 meter, it can be 10 meter error also. So that 5 to 10 meter error can be decreased, and it can come narrow down to around 1 to 2 meters. So without doing anything else, we can just keep open the SBAS facility on in a GPS receiver, and then if we receive the coordinates, then the accuracy in the data will be just 1 to 2 meters. But we have to see my GPS receiver is having SBAS facility. Then if you see ground-based augmentation system, initially people have developed the ground-based augmentation system, and through ND-GPS MF beacons, which is transmitting the corrections, and they can improve the accuracy up to sub-meters. But the drawback is the corrections cannot travel to very large area. It can go to maximum 100 kilometers and so forth. Then HND GPS MF beacons with 4 sites are now transmitting service with an accuracy in the data can come to 10 to 20 centimeter, similar to OmniStar XP model. Then RTK based stations can have local radio transmitters. Then RTK VRS networks, internet and cell phone based, they can transmit the corrections on the GPS receivers like Trimble, TerraSat or Course, continuously operating reference stations. So this was the initially the concept of actually it is GBAS. It is not basically satellite based, it is ground based augmentation system. So there are ground based stations which are calculating the corrections, and then that corrections are transmitted to 50 meter, 50 kilometers, 100 kilometers kilometers and so forth. But the accuracy will be much better. We can achieve through ground-based augmentation system. But overall, what happens? The coverage is not so very large. It cannot go up to complete continent level. And if you see the augmentation means, I'm always talking about augmentation system. Augmentation means enhancing the capability or enhancing the accuracy of a system. So here what is happening with some extra data, what we can generate for a given GPS satellites, with that data we can improve the accuracy of my coordinates. So that is the meaning of augmentation system. So that is the applicability of augmentation system. It enhances the accuracy. It improves the accuracy of my coordinates. So initially it was satellite based augmentation system. Later people went for a satellite based augmentation system. So here you can see for satellite based you may get large range of augmentation system for different regions or at different country level. If you see WAAS, it is called Wide Area Augmentation System. It is developed for USA and its surrounding areas. So we can apply these corrections in USA and its surrounding areas. EGNOS was developed for European countries. It is called European Geostationary Navigation Overlay System for European Union. So in that region, if you open your system, you can invoke EGNOS facility in the GPS receiver. So that GPS receiver will receive these corrections in the European Union regions. Then MSAS, it is called MSAT, Satellite Based Augmentation System. This is working for Japan region. For India, it is Gagan. It is called GPS aided geo augmented navigation. GPS aided geo augmented navigation. This for India and its region. So it is developed by India. So it receives the GPS signals from USA based Navistar satellite, and they calculate the GPS corrections, and then that GPS corrections are uploaded to geostationary satellite. Geostationary satellite broadcast these corrections to a very wide area. We'll see that how much wide that footprint is. Then GRAS is ground-based regional augmentation for Australia. Canadian DGPS, again it is ground-based. OmniStar XP, HP, it is a ground-based, and then Starfire. So some are basically ground-based augmentation system, and now you can see maximum are basically satellite-based. So these are the satellite-based augmentation system, but this one previously it was developed as ground-based augmentation system, and still people are continuing these systems as ground-based augmentation system. Content, if you see, it has lot of information which can be received. Mainly as a layman, I will tell basically they are GPS corrections, basically errors has been identified at the base station, and that errors are received to the master control. From there it is uploaded to geostationary satellite, and from geostationary satellite it is errors are transmitted to wider area, so that these errors can be applied on a rover data, where with these corrections the accuracy of the rover data improves. You can see the principle of satellite based augmentation system through this slide. You can see what is happening here. There are referencing stations like for in India, which are continuously receiving the data from the navigation satellites, and these are the referencing stations. That means we know the actual coordinates of these points, and they are also doing observation every 1 second or every say half a second. So they are getting the data every second rate, and that data is compared with the actual coordinates, and once they compare, they can find out the error in X, Y and Z. The moment they are able to get the error in X, Y and Z coordinate at particular given time, because data is observed every 1 second or every half a second, So every half a second we are getting these corrections. Sorry, and these corrections are then sent to the master control site. So this is the master control station where these corrections are received every 1 second or every 2 seconds, whatever the rate is defined. So, and these corrections has been uploaded from the master control to a geostationary satellite in that region, and then these corrections are transmitted by the satellite in the atmosphere as satellite broadcast, having vector corrections, having use and do not use, and ranging signals. So from this information, this is received by a rover. Suppose there is a rover GPS kept on an aircraft. So these corrections are received by this rover, and rover will improve its coordinates and it can give better information to the pilot. Suppose if it is for takeoff or landing. If you see, Gagan is very initially developed for Airport Authority of India for guiding the pilots during takeoff and landing. Without any extra cost, they can get the accuracy in the coordinates of around 1 to 2 meters. At Cat 2 or Cat 3 landing stage, they use this information and pilot get more accurate in its own position to get an idea how the landing is, how the landing of the aircraft or how the takeoff is going on. So this is the concept way the Gagan or the satellite-based augmentation works. So here you can see the rover is receiving the its coordinates from this signal, but it is also receiving this signal for GPS corrections. So these corrections are applied to the data, what it is using to calculate the coordinates of the aircraft at a particular time. But applying the GPS corrections through satellite-based augmentation system, the coordinates error is decreased and accuracy basically improves to be around 1 to 2 meters. So you can see the role of geostationary satellite. Once there is corrections has been received by the master control site from the referencing stations. So these errors are finally processed in the form of corrections in XYZ, and they are uploaded to geostationary satellite. Then geostationary satellite transmit these errors to a very wider region. You can see it is covering more or less 1/3 of the globe. If you see this much area, this is the footprint coming up for one of the satellite-based augmentation system. Now you can see the different augmentation systems which are working worldwide. Their locations you can see for VAS is for USA and its surrounding regions. Then IIRS for European Union areas, MSAS for Japan, Gagan for India and its surrounding areas, and there are many more. Features of Gagan, if you see specifically, the Gagan is a satellite-based augmentation system implemented by India based on GPS data. And once we invoke or activate the Gagan in my GPS receiver, we can achieve the best in XY horizontal accuracy of around 1.5 meter, and in vertical it is 2.5 meters, because height is less accurate, but still we can see the improvement in XY to be of best 1.5 meter and in Z 2.5 meter. So if you see these geostationary satellite, its life is of 15 years. So same geostationary satellite which is looking towards India and its surrounding regions can work for 15 years. The cost of the project is 7.74 billion, or in US dollars you can see. So SBAS, it's basically based latest configurations for EGNOS, MSAS, VAS, Gagans and so forth. Services means services are determined by number of factors including number and location of reference stations has been installed in an area, actual system design details and environmental conditions. So you can see the actual corrections we are calculating through SBAS. It depends upon the referencing stations, how these stations are working, actual system design details, environmental condition, and where these referencing stations has been installed on the ground. Gagan objective, if you see, it provides satellite-based navigation services with accuracy and integrity required for civilian and aviation applications over Indian airspace. The first application for Gagan was for giving facility to aviation industry in the Indian airspace region. So Gagan has basically in two phases. Initially, if you have noticed long back, it was as a TDS, technology demonstration system. Once it was fully operational, it has been brought now as FOP. FOP means final operation phase. Now it is at final operation phase. That means it is fully operational and working and giving its facility. By July 2013, you can say the qualification test has been done for aviation to check that system is working fine, and later it was made as a fully operational phase. You can see the configurations of TDS elements which has been placed at different locations here as a referencing stations. It has 8 INRES, 1 INMCC, 1 INLUS. Then there is a communication link between different referencing stations and master control. Then there is a ionosphere error corrections to be applied. INRES means Indian reference stations. INMCC means Indian master control, and INLUS means Indian navigation land uplink stations. So these are the components of on the ground of SBAS, which is supporting to generate the corrections, and these corrections are uploaded to geostationary satellite. If we see just the details of INMCC station in Dehradun, which is in, INMCC station developed by ISRO for Gagan. It is a station located at Bangalore. INLUS, basically, it is a 11-meter dish antenna in Bangalore, and it is transmitting uploading the corrections, and with the referencing stations at New Delhi, Bangalore, Ahmedabad, Kolkata, Jammu, Port Blair, Guwahati, Trivandrum, Bhubaneswar, Porbandar, Nagpur, Jaisalmer, Dibrugarh, and Goa, Patna, and so forth. Gagan configuration, you can see the INMCC1, INMCC2, then INLUS 1 and 2, and they are different referencing stations which are basically receiving the corrections, transmitting to INMCC, and from there the data is received at INLUS 1 and 2 to transmit it to the geostationary satellite. So these are the geostationary satellite. These are the GPS satellites of USA, which are basically giving the signals. From the signals, the corrections are calculated on the ground, and these corrections are uploaded to geostationary satellite. So these are the geostationary satellite, total 3 in number. So Gagan FOP, if you see fully operational configurations with the referencing stations, master control, and uploading uplink stations. This is the Gagan coverage over worldwide. If you see from India, this is the biggest footprint up to this region. We can receive the Gagan corrections. You can see up to subcontinent of Africa, Australia, up to European countries, we can receive these corrections. So its footprint is very, very large, approximately to be covering 1/3 of Earth. Advantages of Gagan. Gagan will increase the safety by using a 3-dimensional approach operation with course guidance to the runway, which reduces the risk of controlled flight into terrain. Gagan will also offer high position accuracies over a wide geographical area like the Indian airspace. And you can see the Gagan utilization for precision approach during landing, specifically at the Cat 1 to Cat 3, Cat 2. In this area, the Gagan corrections are very, very important to give very accurate position to the pilot about the aircraft. You can see the Gagan initiative as a for by India. G is called, as I mentioned, GPS-aided geo augmentation navigation. Provides safety of life certified signals in space for aircraft navigation. So you can see when with the help of GPS accuracy, we may have around 10 meter or 10 meters. If you see in feet, it comes to be 30 feet or so. But if we apply Gagan corrections, so you can see the accuracy of around 10 feet, or it can be 1 to 3 meters. Now you can see the advent of satellite technology, effect of on GST and aviation, that is geospatial technology. Basically, with this we have seamless and precise navigation, shorter or more flexible routines, increase in capacity and efficiency, new surveillance technique, ADS-B or ADS-C. We can have better airport utilization with this Gagan facility. We can have a problem at high altitudes is still with the help of Gagan. Concern about the visibility of geostationary satellites at the edge of the coverage footprint. Number of times still some limitation we can see when we are working in very high undulating terrains. So maybe geostationary satellite signal may not be available in the pockets. Reception may be particularly difficult during aircraft maneuvers. Reception is particularly critical during approach and landing. And you can see the current international signal phase for different satellites as well as the SBAS. So you can see for GPS, it is L1 and L2 frequency. GLONASS, you can see its frequency. Galileo, Compass, IIRS has L5 and L1 frequency. Then if you see SBAS, Indian and others, it is basically L5 and L1. So these are the frequencies on which we can receive these corrections. Of course, for IIRS, this is basically your L1 and S band. This I have already explained. If we are using GNSS concept, we have interoperability, so we can use the data from different constellations, and we get much better accuracies. Every time accuracy from the GNSS receivers is always better, because the geometry remains better when we use the satellite from different constellations. We can have Gagan applications in civilian use, in avionic navigation and precise landing system. That was the first application people thought, and people designed the Gagan system. Mapping and in GIS data capture, we may get much better accuracies when we are capturing the GPS data for GIS and mapping purpose. Automated logistics in factories, construction sites and mines, vehicle tracking and fleet management, we may get much better accuracies through Gagan. Terrestrial navigation aid for hikers and the travelers, visual and voice navigation for drivers, integration with mobile phones. This is all about Gagan. Thank you.